Imagine a clock face that represents the times of the day. To keep things simple, let's assume the clock has a 24-hour dial. Let's say that we observed a phenomenon twice, at 5 and 7 o'clock. What is the typical time of this phenomenon occurrence then? Intuitively, the average between 5 and 7 is 6 o'clock. This result has been obtained by simply averaging two numbers. 5 plus 7 divided by 2 equals 6. So what is the average between 23 and 1 o'clock? Counting as before, 23 plus 1 divided by 2 equals 12, but this is noon. Meanwhile, the points in question are concentrated more around midnight, 24 or 0 o'clock. Rather, midnight is the time we would consider the true average of 23 and 1 o'clock. But how was this result obtained? And why does it make more sense? Furthermore, what is the average between 6 and 18 o'clock? Although measured by the cycle of hours, time is not really periodic, avoiding cosmological considerations. So one might object that this example is faulty. However, it's easy to point to the genuinely periodic quantity. What is the typical wind direction in a given place? The direction as an angle is periodic by nature. So how to average angles, and how to do statistics on such periodic quantities? Hello, my name is Karol Ławniczak, and I am going to investigate the problem of mean position on the circle, or mean direction, as an introduction to directional statistics. To begin with, let me remind you the basics of the concept of the mean, as well as some terms related to circle. A viewer familiar with these matters may immediately skip to the next section. Many types of mean are known: arithmetic, quadratic, or root mean square, cubic, harmonic, geometric, generalized power mean, logarithmic, generalized f-mean, and more. Other quantities that characterize center of set, mode, median, midrange, with significance and properties more or less close to these of the mean, are also useful. We call them central tendency measures. Each of them can be calculated from discrete or continuous variables. Weights can also be assigned to individual observations. We will begin with the arithmetic mean, but there will be time for other means and other measures of central tendency. Averaging rely on the summation of the numbers and dividing that sum by the number of addends. When addends are weighted, the divisor is equal to the total of weights. The formula undergoes simplification if weights are normalized to sum up to unity as the probabilities. Each of the formulas listed works well for a multivariate case. You just have to stick to the rules of vector calculus. Please feel free to pause the video now and analyze these matters closely. Depending on how the data is provided, whether they are given in a raw state or aggregated as frequency distribution, they are entered slightly differently into the formulas for the mean. The mean is also the expectation value for a given probability distribution. For discrete distributions, it is a weighted mean calculated as before. For continuous distributions, the equivalent of this formula is valid, where, in the place of probabilities, we have a probability density function, and discrete summation turns into continuous integration. These definitions are specific to variables belonging to the simply connected Euclidean space. In multiply connected spaces, they fail. Let's stick to the idea that we are interested in the direction of the wind. The wind direction is quantified as the measure of an angle from some reference direction. In a geographical context, as the reference direction, we usually pick the north, and the angles measured from it is called an azimuth. More generally, we call this angle an orientation angle. When this is not confusing, we refer to the measure of an angle briefly as angle. Angles are in one-to-one correspondence with arcs on the circle. In particular, when a circle has a unit radius and the measures of the angles are expressed in radians, their values numerically agree with the distances measured on a circle or arc lengths. As an orientation angle is measured relatively to some reference direction, the position on a circle is measured from some point that is the origin of the frame of reference in the one-dimensional space of the circle, or from two-dimensional point of view along an arc. In mathematics, we usually choose the origin of the system at the intersection with positive x-axis and the direction counterclockwise. Note that the angles are identified after going around the entire circle. In fact, you can measure angles with real numbers, but every 2 pi they mean the same angle again. We have to agree to some convention on which interval we will use and bring the angles expressed with numbers outside this range to belong to it again. We can use the range from 0 to 2 pi. We just cut this helical surface along the positive x-axis, and then we flatten one slice of it. However, if we cut the surface along the negative x-axis, we get a symmetrical interval from minus pi to plus pi. This range is the one we will use. The origin of the coordinate system is still on the right, but the branch cut is marked on the left. Someone may still ask why it is not good to calculate the mean normally, and by normally they mean as for variables belonging to the line segment. The introduction should already convince you that the points which are close to each other on the circle do not necessarily have to be close on the segment resulting from cutting the circle open. Now we will look at it once again. Approach number 0. Let's try to calculate the average position of the points on the circle the usual way. Depending on where we cut the circle, we get a different position for such mean. Even though we change the orientation coordinate minus 36 degrees to exactly the same angle of 324 degrees, the mean changed from 49.8 to 121.8 degrees, which indicates a completely different place on the circle. This is not some kind of angles counting trick. The angles indicate the position of the circle, which has a different topology from the line segment. Although the ends of the segment are as far apart as possible, after wrapping it in a circle, they became identified. The proximity of the points and their distances change, though they are still measured along the same line. What was far turns out to be close, and the meaning of the mean lies precisely in the question of distances. Thus we need to take the circle seriously as an essentially different space from a segment. So you cannot calculate the mean on the circle the usual way, because the usual mean of the values belonging to the circle is not unique. There are, however, more reasons to find this approach unsatisfactory. They will become clear in a moment. Statistics on a circle can cover 2 fundamentally different situations. First, we may deal with the position of points on a circle lying on some plane as a figure. Then both the circle and the inside of the disk are of real importance. While the points are only meant to belong to the circle, the inside of the disk is also a thing. We can also deal with directions or angles, as we did a moment ago. Then the circle contains labels referring to them. The circle topology reflects well the cyclical nature of directions and angles. However, only the circle alone really matters. Only its points correspond to the angles, and the inside of the disk has no real-world counterpart. In fact, we can identify all the points on the common radius, excluding the center of the circle, as they correspond to the same direction. However, this brings the entire plane, deprived of the one point, to the circle again. While the first case can be approached from the point of view of the surrounding space in which the circle lies, the second case is inherently circular and topologically non-trivial. Here it is likely to confuse averaging a circular variable with averaging a real variable over the circle as a domain of integration. One thing is to calculate the mean value of the function with values in R or Rd specified for the arguments belonging to the circle. Another thing is to calculate the mean of the function whose values themselves belong to the circle. The former is a simple closed curve integral of a given function, such as the average altitude above sea level on the closed loop route. Only the latter is a kind of mystery. Circular statistics come into play not when the domain of integration is a circle, but when the value of the function subject to averaging is a point of manifold with a circle topology. It's high time for the first serious approach. We will call it an extrinsic mean. It is more widely known as circular mean, for example in Wikipedia, but the name is misleading. I forewarn you that this approach will also prove imperfect. The circle as a manifold is immersed in the plane, precisely speaking embedded. Let's forget for a moment that the space we are interested in is the circle alone. This trick may seem legitimate, as the point location information is conserved. Now we can calculate the usual mean of the positions of these points in two-dimensional space. It is their center of mass. Since the points come from the circle, their Cartesian coordinates are trigonometric functions of the angular coordinate that specifies the position on the circle. Alas, the resulting point lies inside the disk, not on the circle itself. Our mean does not belong to the space where it was supposed to exist. The name extrinsic mean may be a bit surprising, since it is located inside the disk. Yes, it is inside the disk, but outside the circle as a manifold. However, you can project the point perpendicularly on the circle, along the radius. As long as the circle has unit radius, this is equivalent to vector normalization. The same can be achieved with the arc function when we parameterize the points using complex numbers on the complex plane. So we get some mean belonging to the circle. Whether it meets the other requirements for the mean is a separate matter. Anyway, it is clear that the procedure of averaging did not take place in the space of the circle, but outside of it. This must be questionable, especially when the circle contains only labels that refer to directions, and embedding space makes no sense in the real world. Let's look for a definition of the mean that will agree with the usual one on a line and also will work for a circle. Here we have some points on the line and their mean. A good point is to consider what the unique role of the mean is. The proper meaning of the mean, and more generally the center of the set, is that it is in some sense the value that best represents the whole set. The point is that it should be as close as possible to all points of the set. The combined distance between a certain point in the domain and all points of the set can be determined in many non-equivalent ways. They are nothing but well-known measures of dispersion, but calculated not necessarily around the center, but around any point in the domain as its function. We call it the Fréchet function, at least in the simplest case. Specifically, the mean is intended to minimize the sum of the squared distance, weighted if needed, between a given domain point and all points of the set. And, in case of our dispersion function, the center is known as a mean. It should be noted that this approach reverses the conventional order in which descriptive statistics are defined. Usually, the mean is taken as the primary, and the variance is introduced as the average square of the deviations from the mean. Meanwhile, here we calculate the Fréchet function, which is actually the modified variance, calculated around each point in the domain, and then the point that minimizes this function is considered the mean. In fact, it does not matter whether we use sum of squares, mean square, root sum of squares, or root mean square. Since the quadratic function is strictly monotonic for positive arguments, they all are minimized by the same argument. In case of continuous data, we have to replace weighting factors, probabilities, with probability density function, and turn discrete summation to integration. One can also consider minimizing another measure of dispersion, especially the sum of distances, in the power of 1. This is how you get the median. This is a crucial observation. Until now, you have probably treated the median as a positional measure. In order to compute it, you had to arrange the values in ascending order and point to the middle position. Meanwhile, for the mean, we had a closed formula. Now you can see that the mean and the median can be treated the same way, and the corresponding formulas just differ in the exponent of the power. The conclusion is relevant not only for circular statistics, but also in general. The other measures of dispersion will yield different measures of central tendency. As can be seen, there is a metric in these variational definitions. What kind of center will be obtained depends on the choice of the metric. The measure of central tendency depends on both measures of dispersion and metrics. Let us temporarily restrict ourselves to the power function for measure of dispersion and to the Euclidean metric. Then the measures of dispersion became the respective p norms. For p equals 0 and infinity, the formulas must obviously be understood in a sense of the limit. The L0 function is not really the norm. Interestingly, the dispersion measures L0 and L infinity are also defined for variables belonging to discrete domain, even nominal variables. It is known that the center defined using L2 dispersion, mean, and L infinity, midrange, are unique, while L0 mode and L1 median need not be. Again, we can use a measure of dispersion in more than one form, but since G have to be strictly monotonic, they all have a minimum at the same place. Now, when we know the variational definition of the mean, let's take another look at the extrinsic mean for a circle. Of course, the usual two-dimensional mean on the plane can also be obtained via a variational approach, but since we have a closed formula, it is not optimal way. We need a mean that is truly the mean on the circle. It should minimize the Fréchet function, but with distances measured along the circle itself. It is convenient to express the position on the circle in terms of complex numbers. In the standard representation, the real and the imaginary parts correspond to coordinates in a rectangular coordinate system. Polar coordinates are more natural for a circle. The radial coordinate is the modulus, and the angular one is the argument. A circle is a set of points corresponding to numbers of the same modulus. The position on it is determined by the argument, or rather, the entire phase factor, that ensures the cyclical behavior expected from the coordinate indicating the direction. We may impose a condition on angles to belong to the preferred interval of length 2π. Here we have chosen it from -π to +π. In general, I advocate treating complex numbers simply as a formalization of the concept of rotation and scaling in a plane. An excellent discussion of this topic can be found in the linked video. However, we can do without complex numbers, but then the angular coordinate must be consistently treated as a number modulo 2π. Clearly, the ordinary difference in angular coordinates is not a good measure of distance on a circle. Just consider the distance between the points with coordinates -165 degrees and +165 degrees. To automatically take into account the topology of a circle, you can take advantage of the properties of complex numbers that have it embedded in their construction. Subtraction of the arguments of complex numbers corresponds to division of these numbers. Division of complex numbers with modulus 1 is an operation that is always well defined and closed. You can also write this without the arg function. The complex logarithm has been chosen so that the result belongs to the range we use to parameterize the angles. For the interval from -π to +π, we choose the branch cap the usual way, from -∞ to 0. Most often, we use the metric squared. Of course, you can do without complex numbers, but at the cost of switching to modular arithmetics. If we want to stick to the range -π to +π, some π components appear. We insert the metric squared into the variational formula known from the linear case and, voila, we can use it on a circle. The plot of the Fréchet function no longer has a simple parabola shape, but it must have a minimum somewhere. This is precisely where the intrinsic mean is located. This point belongs to the circle. It represents the whole set well, as it minimizes the sum of the squared distances to the set points, and these distances are measured along the circle itself. We can see that this is a fundamentally different concept to the extrinsic mean discussed previously. The combined information from these charts may also be presented in three-dimensional form. One may ask if the projection of an extrinsic mean on a circle can be obtained by some variational formula on the circle itself. Well, it can be, but with the use of an appropriate metric. It is a Hordal metric that measures the distance not on the circle, but along chords passing through the inside of the disk. In this sense, intrinsic mean and extrinsic mean projection simply differ in metrics. The intrinsic mean employs an intrinsic metric on the circle. A significant weakness of the formulas found lies in the arg-mean function. These are not closed analytical formulas that compute phi bar, but only allow you to compare the candidates and search for the mean numerically. Fortunately, there is a way to calculate the intrinsic mean efficiently, at least for a discrete data. Let's try to transform the usual mean formula to accept and return not angles, but entire phase factors. In order to do this consistently, angles addition should be replaced with the multiplication of the phase factors, and division of an angle with the appropriate root. The problem is that the root of a complex number is an n-valued function. We can bring out the angle itself. It is not unique, but there is n distinct values. Noting the usual mean in this formula, we can rewrite it as follows. Phi bar 0 plus k times 2π divided by n, where phi bar 0 denotes the usual mean, and k are n subsequent integers. Again, we can do without complex numbers. We just have to remember that each angle is defined modulo 2 pi. The result is of course the same. Here are the points found. There are as many of them as there were points to average. However, the mean should be 1. We need to compare these points in terms of how well they represent the set. To do this, we calculate the Fréchet function for each of these points and choose the one for which the score is the lowest. The search for minimum runs over n points. Equivalently, we can say that the search runs over n indices. This approach has the advantage over the former variational one that it requires the comparison of only a finite number of analytically determined candidates, and not a numerical search for values on a continuous scale. The one true mean has been found, and it happened in as many steps as there were points to be averaged. We can see that all points suspected of being the mean, by virtue of the properties of the complex root, form a regular polygon inscribed in a circle. Surely, you remember that the usual mean of the angles is not defined unambiguously, and depends on the choice of the angle value range. In fact, all its possible values are among our points suspected of being the mean. Let's also see how the Fréchet function looks like for the rest of the domain, not just suspected points. Interestingly, some of the suspected points lie in the local minima of Fréchet function, and others do not. Finally, let's see both kinds of mean on the circle. Indices numbering the suspected points can be chosen freely, as an arbitrary subsequent integers. However, for the order of points to be consistent with the chosen range of angle values, the indices must be selected purposely. The case of the mean of 2 points is somewhat trivial, with only 2 points, intrinsic mean and extrinsic mean projection always coincide. Let's see this with a few random examples. While changing the mutual position of the points, we observe how the Fréchet function and the position of both means change. Without losing generality, we consider the position of one point as the origin of the system and manipulate the position of the other. With 3 or more points, both types of mean generally do not coincide. While the dependence of a certain state of things on one variable is easy to present with animation, presenting its dependence on 2 variables is more troublesome. After all, time is one-dimensional. However, let's propose a trick. Let the rate of change of the second variable be several times faster than the first one. Then, for the first variable to run through its entire range of variability, there are multiple runs of the second one through its own range. In this way, each value of the second variable is performed at different levels of the first one. Such animation gives a good picture of the state of things under study for all combinations of the 2 determinants. Let's see how the situation changes with the number of points, beginning with the trivial 1-point case. The method of presentation introduced a minute ago may be extended to deal with more than 2 variables. A natural question arises: when, if at all, can we use the usual means and the other well-known statistical tools as an approximation to the circular statistics? It turns out that the answer is quite simple. When the discrete data points are concentrated in one area, simply cut the circle open away from the area of concentration and proceed as in the Euclidean case. You will then get a fair approximation of the mean on the circle. It is worse when the points are scattered around the circle so that no clear cluster can be distinguished. When we deal with a continuous probability distribution, its form on the antipodes of the cluster is decisive. If the density fades there out, the Euclidean approximation will be fair. However, if the distribution there is closer to uniform one, the Euclidean approach does not correspond to reality at all. Both the extrinsic and intrinsic mean have their counterparts based on L1 norm. Therefore, we can distinguish the extrinsic median, the geometric median on the plane calculated from the points from the circle, having its projection on the circle itself, as well as the intrinsic median defined purely inside the space of the circle. We had a close formula to find n points suspected of being an intrinsic mean. Unfortunately, we do not have something like this for the median, and we are left with the variational approach. The more important median for us is the intrinsic one. The intrinsic median of an odd number of points always coincides with one of the points. When the number of points is even, the median lies on the arc joining the three of the points. Only in case of 2 points, median lies on the shorter arc between them. We know a similar situation from the linear case. There, for an even number of points, the 2 middle positions, as well as the segment between them, were equally good candidates for the median. Often it is assumed that the median lies halfway between these points. But this is only a disambiguation condition. It does not follow from the variational definition, and we will not impose it. Moreover, we are dealing here with an arc covering typically 3 points. We have to accept the fact that for an even number of points, the intrinsic median on the circle is not unambiguous, even locally. Let's go back to the odd case. Of course, the intrinsic median does not have to coincide with the intrinsic mean, and it predominantly does not. What about the extrinsic median? Of course, it is calculated in the space in which the circle is immersed, that is on the plane. The median on the plane, or more generally in the d-dimensional Euclidean space, is known as the geometric median. We don't have the closed formula here, the kind we had for the mean on the plane. Therefore, we are left with the variational approach. The median is simply a domain point that minimizes the sum of distances in a power of 1 to all points of the set. Properties of the extrinsic median of the circle points rely on the properties of the median in the embedding space. Let's look at the properties of the geometric median itself in the well-known Euclidean space of dimension from 2 upwards. This is crucial if the points are collinear or not. When the points are collinear, it comes to the usual median. If there is an even number of them, the geometric median is ambiguous, even locally. Each point on the middle segment is an equally good median. The dispersion function L1, sum of distances, is constant there. Therefore, each point in this range of arguments is a minimizer. Typically, a somewhat artificial disambiguation condition is introduced, but we don't do that here. The unambiguousness of the median in such a case can be saved when the middle segment is degenerated to a point, that is, when this point occurs at least 2 times. This corresponds to weighting the points, that is, assigning them certain probabilities, this way only rational ones. If there is an odd number of points, the geometric median is unambiguous and coincides with the middle point. For arguments on the circle, there can be up to 2 different collinear points. In such a case, the geometric median is always locally ambiguous, and all horde points between these points can be appointed a median. Or the same point can appear multiple times in data set. This corresponds to weighting the points. Then the median will coincide with this point, which is counted more times. When both points are counted the same number of times, the median becomes locally ambiguous again. An unexpected advantage of the geometric median in Euclidean space of dimension from 2 upwards is that, as long as the points are not collinear, the median is unique, regardless of the number of points. The median of 3 points lies at the Fermat point. When the 3 points form a triangle with an obtuse angle over 120 degrees, the median lies at the vertex of this angle. Suppose none of the angles is 120 degrees or more. In that case, the median lies inside the triangle at the intersection of the lines joining the vertices with the vertices of a equilateral triangle constructed on the bases of opposing sides. The median of the 4 coplanar points lies at the radon point. If one of these points lies inside the triangle formed by the others, the median coincides with this central point. If, however, the points form a convex quadrilateral, then the median lies at the intersection of its diagonals. Of course, in general, the median on the plane does not coincide with the mean on the plane. Sometimes the median on the plane lies inside the disk, but sometimes it also belongs to the circle itself, and not only in somehow degenerate cases. When necessary, we define its projection on the circle the same way as in the case of the mean. How do the medians compare to the means? The intrinsic median has been created by minimizing the dispersion function L1, and the mean using L2. On this plot, the L2 dispersion function, the Fréchet function, has been transformed into its root to bring both dispersion measures to the same units. The vertical axis is scaled accordingly. The locations of the means are marked with squares and the medians with hexagons. The intrinsic measures are distinguished by green and extrinsic ones orange. The projection of extrinsic measures onto the circle is indicated with arrows. Much could be said about the median on the circle and the median in general, but somewhere you have to say stop. This is a good topic for a separate video that may be made in the future. Then perhaps I will talk about quantification of dispersion and more about doing statistics on circular variables. Particularly interesting is the problem of the normal distribution on the circle and the sphere of arbitrary dimension. Indeed, in perspective we have statistics on the sphere, which brings challenges other than those on the circle. In principle, each topologically distinguishable manifold have its own statistics. Some of them, like the circle and the sphere, are of great importance. Actually, I don't like questions like, what do you need it for? The cognitive curiosity alone should be enough as a motivation. However, I will give an example of employing this machinery to work. Moreover, it will be a par excellence physical one. Indeed, the indication of the mean wind direction is already such an example. But come on, I know that you are counting on some solid contemporary physics. We know very well what importance the expectation values have in quantum physics. Consider the wave function, in the Schrödinger image and in the position representation. The probability density is the squared modulus of this function. The position of the particle is unobservable. We find its expectation by calculating the mean value of the position with a given probability distribution. Suppose the generalized coordinate is an angular variable. So how to determine the expectation value of such position, in fact an orientation? There is currently no satisfactory theory of quantum mechanics on topologically non-trivial manifolds. It is the different rules of statistics that have a lot to do with it. Nevertheless, we already know how to calculate the mean position on the circle. Here we see a density of a Gaussian coherent state on the circle for zero angular momentum. The Fréchet function and both types of mean are depicted as before. A higher angular momentum slightly spices the picture up. Which of the physical properties of the expectation value known from the trivial case our mean retains and which it does not is a separate matter. This is by no means a simple field. Since you've made it to this point, indeed the topic has proven interesting to you. If you do not want to wait for the next video or would like to go into details specific to the scientific paper, please use the links in the description. I will try to supplement the list, so I encourage you to check back from time to time. There will also be additional materials available. Thanks for your attention.